All right. So in this case, I want us to consider our AC theory, which is the part of our RL series circuit. It is very, very important that you have a recap of this. In your N5, you'll find out that you are working with AC theory, where you are going to be given the first part, the basics of exact. This is like almost what you had from your N3. There is nothing new that you are actually going to consider as long you are to work with series RL circuit. Okay, so as we do understand from our previous case that we had in our N3, if we are given a series RL, we're going to have something like this. That's a resistor and an inductor. So you shall be having a resistor and an inductor, let's say connected to a voltage source. Just going to have a sketch in that case, which is alternating. So definitely you'll be having the total voltage here and also the frequency, which is taken in hertz. This is our resistance and this is our inductor. We do understand that on this circuit that we are having, the current is the same. There's a series circuit where the current is the same, the current that is going to flow here, which is referred to as the total current from the supply. It is the same current that is going to affect the resistor to give us a voltage drop across the resistor. So you see that you'll be having a voltage drop across the resistor and also a voltage drop that you are going to also obtain across the inductor, which you're going to call VL. So there is a voltage drop. So we understand as we are dealing with the AC theory, the sum of the voltages is referred to as the phasor sum whenever you're talking about this total voltage. All right, let's talk about this total voltage. The total voltage VT, it is not equal to the sum where you simply add VR and VL like what we had when dealing with the DC, when you're dealing with those DC circuits. No, this one is referred to as the phasor sum. The phasor sum. When they're talking about the phasor sum, you understand it much better if we are to put it on a phasor diagram. Remember, guys, I'm just gonna give you a hint of what you had back in your N3. Remember when you're using that civil concept. Okay, remember when you're using that civil concept, you're concentrating with the part of an inductor. All right. So when you're dealing with an inductor in this case, considering this is the inductor that we are given here. Okay. So what is going to happen between the voltage for this? We can see that the current lags the voltage, meaning to say the voltage leads in this case here. The voltage leads the current. So the voltage is on top when you're considering the voltage. Since the voltage leads, it is going to be on top like this. Just want you to see where these formulas were taken from. We had it from N3, but at least if we have this, we can at least have a better understanding. So if it is the phasor sum, if it is that the voltage leads, it means the voltage is going to be on top. We're going to see that VL will be on top like that. That is the indication of an inductor. If you still remember those things. Okay. Now we are saying, since there is a resistor, it is not going to be directly at 90 degrees like what we are used to. When it is like this, we have got our VC at 90 degrees. It is when given a purely capacitive. Remember your N3, when you're dealing with a purely capacitive. It was a purely capacitive, purely inductive, whatever that you are given. So in this case, sorry, we are getting with an inductor at VL on top. So when you're given a purely inductive one, you have it like that at 90 degrees. But now there is the voltage of the resistor and that of the inductor. So they will be separated by 90 degrees by the angle theta this time, sorry. So we're going to have our VR and our VL, but separated now to give us the total voltage by an angle theta. It's no longer at 90 degrees like this. They will be separated by a certain angle theta, which is the phasor, the phase angle that you'll be having from our phasor diagram. We'll be having the theta there, representing the phase angle. So when I'm talking of the phasor sum, this is why I said you can understand it better here. This is what you had. This is your VT. Let us go back to our mathematical presentation. If we are to take it down, it simply means here, if we are to take it like this, I want you to see what we're going to form. We're going to form a right angle triangle here, which simply represents that the distance from this point, the origin here, to this point here, the distance is the one that is represented by our VR here. So our VR is going to represent this distance from this point to this point. The VL going up is the distance also here going up. That is where your VL is. Okay, just want you to see where this is coming from. This one at 90 degrees, this VL is going to be taken straight because it's going to be like a rectangle concept. So this side and this side will be equal. So meaning to say, we'll be having VL here. VT, this one, is the representation of this line, this one. It represents VT. So meaning to say, that's our VT that we are seeing here. Just like that. So what are we forming here? A right angled triangle. Let us go back to our Pythagoras theorem, because when you talk of the phasor sum, we are talking about the total, this one. How do you calculate it? It's a right angled triangle like this. How do we calculate VT given VR and VL from our Pythagoras theorem? Remember, if you are given that concept of A, B, and C, it states that C squared is equal to A squared plus B squared, hypotenuse. And our hypotenuse is the voltage, VT. So the total voltage is equal to what? A squared plus B squared. Our A is going to be VR. So that will be VR squared plus B squared, which is our VL. So that will be our VL squared. What you need is VT, not VT squared. So how do you remove this square? Just going to introduce the square root, introduce the square root, introduce the square root. So you remain with your VT like this as the square root of VR squared plus VL squared. It's no longer just a sum where you add to say just VR. So that is where this is coming from whenever I talk of the phasor sum of the voltage. It can be of the impedance, because the impedance still offers the same thing. This will be your Z, this will be your R in this case, and this will be your XL. So it can be the same thing. So it will be R squared plus XL squared. So guys, that is where those formulas are being taken from that we've been given throughout our N2, our N3. I just thought that it is be important that we just do understand that. Anyways, we do understand this, guys. Let us just quickly, right? So we saw that the VT will be the square root of VR squared plus VL squared, which is referred to as the phasor sum. Is the phasor sum of the voltages, okay? So there are a lot of things that we need, guys, on an inductor. We also talk of the reactance of the what? The reactance of the inductor. So this is our phasor sum. We can just write it total voltage, actually, no problem. That's our total voltage. Okay, so there we're gonna have the total voltage. That's the total voltage, and we consider VR and VL. In this case, we're gonna consider them VR and VL over the inductor. All right. Having also the reactance, we're gonna talk of XL, the reactance of the inductor, guys. Remember your XL, that is 2 pi FL. With the reactance, also the resistance, we can able to calculate these voltages. They can ask you to calculate the voltage across each component, meaning to say you can talk of the voltage across the resistor. Since this is a series circuit, the current is the same. So considering that the current is the same, gonna say that voltage will be simply current times resistance. That's the total current times resistance. The voltage across the inductor is going to be also the total current times the reactance of the inductor. The resistance that we talk about is what? Is the reactance. So it's going to be times XL. We have got our total voltage, which is the voltage drop across the inductor, the voltage across the resistor. You can have all those things. You can talk of the total current from the total voltage over the total impedance of the circuit. So how do you calculate that total impedance Z? The same way that you calculated your VT is this case is the same way that you calculate your Z. So Z is going to be the square root of R squared plus XL squared, the reactance of what? The reactance of the inductor. So we have got the total impedance of the circuit. And you also talk of the phase angle. You'll see it that when you're dealing with this, you'll be having, just like I presented before, this will be your Z, this will be your XL, this will be your resistance. So you see that the theta is here, which is our phase angle. So you can talk of this phase angle in terms of XL and R. We can talk of this in terms of XL and Z. We can talk it in terms of Z and R. So it's the way that you write the phase angle, guys. It's up to you. Okay? Since mostly you have the resistance and also the impedance, you can have it as theta. As we can see, this is adjacent and this is hypotenuse. Which ratio? That is the ratio of cos. Cos theta is adjacent over hypotenuse. So if the cos of theta is equal to the adjacent, which is the resistance, over the hypotenuse, which is Z, that means we can have our phase angle theta. So therefore, our theta is simply equal to arc cos of R over Z. Just like that. We can work it from this opposite over adjacent, meaning to say we're talking of tan. Arc tan XL over R. You can talk about anything that as long you are referring from that diagram. So meaning to say in this case, you will be having the phase angle. There's so many things that you can relate. Then the phasor diagram, like I said, the phasor diagram, it's up to you guys on the part of the phasor diagram. What are you going to use? What are you going to use on the phasor diagram? That will be up to you. Are you going to work with the voltages? If you work with the voltages, you're going to have VR and our VL. Then the total voltage, as we saw, is going to be here, having an angle that is separating there, where we know that current is in phase with what? With voltage, with VR. So this can be given in terms of the impedances. Maybe you have the impedance, meaning to say you'll be talking of XL on this side, you'll be talking of the resistance, and here you'll be talking of the total impedance separated by angle theta, depending with the information that you're given. Are you having all? Are you having VR? Are you having VT? Are you having VL? Use that one. Are you having R, Z, and XL? Use that one to represent your phasor diagram. So as you can see, it's just simply our N3 as it is. So this is what you're given in this case, calculating the values of a series RL circuit, a coil with a resistance of 25 ohms, inductance of 0.15 are connected in series to a supply voltage of 100 volts, 50 hertz as shown in Fig 2.10a, which is this one. So we're already given the diagram. That's a series RL, as we can see, the resistor and the inductor, and we're given the voltage and the frequency there. So from this, the question was, calculate 1.1, the total impedance of the circuit, the total impedance of the circuit. So how are we going to obtain the total impedance of the circuit, which is Z? So as we saw, guys, we can obtain this from the phasor sum. We have got R squared over XL squared. So that is our total impedance of the circuit. So Z is simply equal to the square root of R squared plus XL squared. But are we having XL? We do not have. So we are supposed to calculate XL from the inductance. So remember that XL is 2 pi FL. So that's it. Gonna just substitute. That's 2 pi times the frequency, which we are given, the 50 hertz, times the inductance, which is 0.15. So with this, you are going to obtain XL which is the reactance of the inductor. That was going to give us 15 pi, which is same as 47,124 to 3 decimal places. So the moment that we've got our XL, we can calculate our Z, the total impedance, the square root of R squared, resistance squared. That is 25. So it's going to have 25 squared plus XL squared. We have our XL here, which is 47,124 squared. So that was going to give us the total impedance of the circuit. Okay, just use your calculator properly. Going to have 53,345. So that was going to be like this in ohms. So we've got the total impedance there. Then the total current of the circuit, as we can see, can obtain our total current if we've got total voltage and total impedance, which is the impedance of the circuit. We have got everything in that case. So you can calculate the total voltage. Okay, so that's 1.2. I mean the total current. So the total current is just going to be total voltage over total impedance, which is the Z that we got from our calculations. So that's the total current. The voltage is 100 and the total impedance is given there. So let us take our total impedance, 53,345. All right, just like that. So this was going to give us the total current. So if you're going to divide, that was going to give you 1,875 amps as the total current of the whole circuit. This one. Meaning to say, in a series circuit, this is the same current that we have across the resistor. This is the same current flowing across the inductor, which is given as 1,875. So it's going to affect the resistor. It also affects the inductor in series. Current is the same. So on the voltage drop now, across each component, it's going to be easier because we have this total current, which is the same, like I said. So it's going to be easier for us to calculate this. So 1.3 on each component. So we talk of the resistor, going to have the voltage drop of the inductor, going to have the voltage drop. So across the resistor, you can simply use the total current times the resistance. That's we've got the voltage here because the current is there, resistance is there. For current is the same. So simply the current 1,875 times our resistance, which is 25. So that was going to give us the voltage across the resistor, resistor. So this was going to give us 46,875. That is 46,875 volts. Across the inductor, we need the reactance. And if you remember, we calculated the reactance across the inductor. So meaning to say, we can have the voltage in that case. So for the inductor, it's going to be VL, which is the total current times XL. That is, VL is the total current. We have the total current because current is the same. That's 1,875 times XL, the reactance of the inductor. You use the reactance, guys. Remember, that is 47,124. So just like that, we are going to obtain the inductive voltage that is affecting there, which is going to give us 88,358 volts. Okay, like that. So we have the voltages now. Then from there, we need the impedance phase angle. The impedance phase angle, that is the phase angle. Remember, we said we're going to take this from what? Impedance. That is arc cos R over Z. As long with the resistance and the total impedance. That's why it's even called the impedance phase angle. So from the resistance and from the impedance, we have the impedance there. So I'm just going to write it here, guys. That's 1.4. So we saw that theta is equal to arc cos resistance over impedance. So that is, we have the resistance on our circuit, that is 25. So we're going to have our phase angle theta as arc cos R, which is 25 over the total impedance that we calculated. That's 53,345. That is going to give us theta. And that is, guys, make sure you use also your calculator properly. Arc cos, that is shift cos. Remember that from your mathematics. So that is just going to be like this. Let me just quickly have it here. So it's going to be shift, press the shift cos. So that is arc cos 25 over 53.345, like this. All right. So that is going to give us 62.053 and so on. So you can even round off to 3 decimal places, shift, setup, go to fix on number 6. So you're going to fix to 3 decimal places, you press 3. So it's going to be 62.053. So that was going to give us 62.053 degrees at the end as our phase angle. Just like that. Then the last part, they need you to draw the phasor diagram. Draw the phasor diagram. So like I said, the phasor diagram, you're going to relate, because there are 2 things that you can relate, is it from the impedances, the whatever that you're given. You work with what you have. If you have got everything, in that case, like you have the total voltage, you have the VR, the VL, use that. You have R, Z, and XL, use that. So in this case, if you are to check, we can use anything because we've got the voltage across the resistor, the voltage across the inductor, the total voltage is there, the impedance is there, XL is there. So that one, it was going to be up to you guys. Which one do you want to use? Okay, are you going to work with the voltages, or are you going to work with the impedances? All right, so in this case, working with the impedances, this is what we're gonna have, number 2. So the diagram is still gonna be on the same side, whether it's for the voltages. So number 2, in this case, I'm gonna use for the impedances. So the phasor diagram. So like I said, there you choose any part that you want. Okay, choose any part that you want to work with. All right, so let's just stop, guys. This network is going to allow us to finish here the phasor diagram. Okay, so this is it. Like I said, I'm gonna work with the impedances. We saw that it's gonna be like this from our presentation. We're gonna have our XL, of which we calculated this XL. This is the one that we have here. So XL is equal to 47. That is 47.124 from our circuit, which is 25. So the resistance is going to be here, which is 25 ohms. Remember the resistance and voltage. Okay, this will be just in phase like that. Then we're going to have, okay, then this side we're going to have the total impedance. Okay, that is our Z. Our total impedance Z is given 53.345. That is 53,345 ohms. Okay, and the angle, which is the first angle separating in between here, theta, that is the theta that we calculated, which is 62,053 degrees. So that is the idea there of the phasor diagram. So like I said, it will be up to you. What are you going to use? Okay, it will be up to you. Like, what are you going to actually apply in your calculations? You can work with the voltages where you'll be having your VR, your VL, and the total voltage. So you just have to indicate that. It's not even a problem when working with the phasor diagram. So this is what you just need to work with. Let us just revise our basics of N3. So you see that most of the part of that you're going to have, it is just a repetition of your N3. Just make sure you revise everything properly of N3. Then you just take 1 or 2 things that are new, but the basics and everything is simply the same as what we had before.